Hi folks, my name is Scott Mabin and I work on the Rust language enablement team. And today I'm going to talk about Rust on Espressif chips. So what I'll cover today is what Rust is. I know many of you are probably unfamiliar with Rust, or you may have heard of it, but you don't know why you want to use it. Why we're Espressif adopting Rust and starting to use it and support it. What you can do right now with Rust and Espressif chips, and what's the forward outlook with Rust and Espressif chips. So a background on Rust. Rust is a systems level programming language with the slogan fast, reliable, productive, pick 3. They actually sunsetted this slogan, but I like it too much, so I keep it in these slides. The 1.0 release was back in 2015, so it's relatively young, and it has a fairly rapid release cycle of once every 6 weeks. It was previously governed by Mozilla, but since I think about 2 years ago, it's been transitioned to the Rust Foundation. So why Rust? It compiles down to machine code just like C or C++, so it's very quick and efficient. There's no garbage collection. Memory is deallocated as it goes out of scope. This is obviously the case for the stack, but also heap memory is deallocated on drop, so there's no manual need to call free like you would in C or C++. It eliminates a whole class of memory and synchronization bugs at compile time using the type system and a number of subsystems within that. So Microsoft announced in 2019 that over 70% of their CVEs in the last 12 years were related to memory misuse. So you can see why Rust is very appealing to the likes of Microsoft and things like that, and companies like that. Package management is built into the language, and there's a tool called Cargo, which those of you are familiar with ESP-IDF component manager, it's like that, but obviously supports the entire language instead of just IDF components. And finally, it's a imperative language, but with strong functional elements. And if you ever look at any Rust code, you'll start to see that. So why Rust at Espressif? We see it as an emerging language in the embedded and tooling space. So for example, the IDF installer for Windows is written in Rust. So we're not just thinking about it in the embedded context, but also tooling. We expect to be able to write new parts of ESP-IDF in Rust, and we also expect to be able to rewrite certain parts of ESP-IDF which are a bit tricky to maintain in C, particularly some parsing code. Rust has a diverse and large open source ecosystem, and this ties in with package management because it's extremely easy to grab packages from the community. So why Rust for embedded? Obviously, memory safety is an important thing in any application, but memory safety is even more important in embedded systems. On a desktop, the worst case is usually you're going to crash the application, you'll get a seg fault, and the MMU will protect you in that sense, so it won't crash the kernel or anything. But in embedded systems, this is generally different, and you're probably going to end up rebooting the chip if you do like a null pointer dereference or something like that. So Rust's compile time elimination of those bugs is extremely helpful. There's native async support inside the language, and when I say native, I mean it's part of the language. It's not a add-on. And I'll go into a bit more detail about that later. Rust made the active decision to split the core library from the standard library, and the core library is essentially a freestanding library that describes anything that has it makes no assumptions about the environment it's operating in. So it doesn't assume threads, it doesn't assume you can allocate, it doesn't assume there's networking. that's where the standard library comes in. It makes those assumptions and builds on top of the core library. This means it's easy to create targets that just target the core library, and then in the situation where you have threads, mutexes, etc., you can then target the standard library. Again, package management is very useful. So we have ecosystem-wide interface crates like embedded HAL, and this describes how certain embedded interfaces like SPI, serial, GPIO pins should interact. What that means is drivers and HAL implementers can depend on embedded HAL, and that essentially forms a contract as to how the interfaces work. And what that means is you can then mix and match any HAL, so basically any chip that implements embedded HAL, with any driver, so temperature sensor, a accelerometer, anything like that, and it just basically works, which is really nice. And usually in C or C++, you need to have some glue code that every driver would have a slightly different way of setting up this glue code. So it's nice that it is done for you. There are also some other crates like Heapless, which is a non-allocating data structure crate. I know it's a bit of a rite of passage when you start an embedded C project, you write a queue because you obviously need one. But it's nice to just be able to drop Heapless in your cargo.toml, and you have access to a correctly implemented queue, and they've got loads of other things like a min heap, a linear map, I think even a hash map with a efficient hashing algorithm. And there's 1,000 more on the awesome embedded Rust list, and also you can search crates.io for no STD, and you'll find crates suitable for embedded. So what's possible right now? So we currently support 3 approaches with using Rust on Espressif chips. So we have the ESP-IDF project, but you want to use a bit of Rust, a Rust project that you want to utilize ESP-IDF, and bare metal Rust or pure Rust. So ESP-IDF plus Rust. This is for the situation where you have an existing project in ESP-IDF, or perhaps you don't want to write the whole application in Rust. We have the option to create ESP-IDF components in Rust. And because Rust has good interop with C, you can just expose the C interface to the rest of your application. This is particularly useful for things, like I said earlier, like parsing. Rust has very nice tools for parsing strings and parsing just general data formats safely and efficiently. So you may wish to write a Rust component that does a specific amount of a certain amount of parsing for your application, and pass the result back to through the C interface to the rest of your application. Then we have the Rust on top of our ESP-IDF approach. So fortunately, ESP-IDF has a newlib component which the Rust standard library can use to basically interact with ESP-IDF. And this means that you can build the standard library for ESP-IDF, which means you get threads, mutexes, networking, and more, which is really nice. On top of the standard library items, though, we can also leverage the peripheral drivers and other components that exist in ESP-IDF. So by writing Rust wrappers around the raw C interfaces, we can essentially call into ESP-IDF and drive peripherals or certain other components that you may wish to use from Rust. Then we have the bare metal approach. So bare metal programming in C and C++ isn't particularly common, and I would say especially so for R chips. I haven't seen any conscious effort for programming in bare metal in C for our chips. It may exist, but in Rust we're trying to support this, and one of the main reasons is the fact that async is supported by the language and doesn't require any allocations or anything like that. Async in Rust basically compiles down to state machines. And the reason why this is important is because with async, you can have efficient, safe multitasking without a scheduler or anything like that. Typically in bare metal applications, you're generally limited to one, a single thread that does a load of things in one go. And it becomes quite unwieldy to manage that, whereas async really helps there. So a bit more background on async if you're unfamiliar with it. Async is a form of cooperative multitasking where tasks, and I've put tasks in quotes here to not be confused with FreeRTOS tasks, which are essentially threads. Because obviously in FreeRTOS there's a stack size and the scheduler will swap out the threads. This is not the case with async. When async tasks get to a certain point, they will say, come back later, I'm doing something that's going to take a while. And they manually yield the processing time to something else that may be able to continue. Or in the case of some of the embedded executors that exist in Rust, if there's nothing to do, you can just put the chip to sleep until an event wakes it back up, which is really quite nice. So async in Rust adds two new keywords. The async and await keyword, where async defines a block or a function to be asynchronous, and await defines yield points within that function or block. And so here we have the example, asynchronously writing a message to a UART here. So the yield points are wherever you see a dot await. So in this instance, you would set up the message, queue the bytes to be written to the UART, and then await. And behind the scenes, what this will do is, queue up either a DMA or shove it in the FIFO and wait on an interrupt. And then during that time, the executor can go back and try and do something else until this is woken up. And then obviously the next line, and then another yield point there. So what async is not, I've seen a common misconception when developing an application that is either blocking or async. I don't think this is the case. I think async and blocking can and should be used in conjunction with each other when you can. It's perfectly valid to have a fully async application or a fully blocking application, but mixing the two together can yield some really cool results. So an example of that would be async in an RTOS environment. You may think when you have threads, async may seem redundant because threads are your concurrency model, but it can be used to reduce your memory usage through stack sizes and sometimes even power usage. If you know that you've got nothing to do, the scheduler can put the chip to sleep. So take an application that has one heavy computation task and three smaller IO bound tasks. In a traditional thread-only based model, this could use up to 4 threads with varying stack spaces. Combining the async and blocking approach, however, you could reduce this to just 2 threads, one for the heavy computation that you don't wish to be interrupted very often, and another which asynchronously multiplexes the other 3 IO-bound tasks. So what you may find is you've probably written something like this asynchronous multiplex task, where you just have a util task that checks 3 or 4 different things, as opposed to them being separate tasks in the sake of saving stack space. What's nice about async is that the compiler writes this state machine for you, which is really cool. And I find, like, just coming back to this example, the execution flows in this order, which logically makes more sense when reviewing code. Even though it may be doing things in between this, there's no chance that write bytes, that goodbye could come before hello world. So onto chip support. There's one limitation for all the projects, so bare metal and ESP IDF projects, and that is if you're targeting an extensor chip, there needs to be support in our LLVM fork. And because of our LLVM fork, we also have a forked Rust compiler. So if you're targeting extensor, which is the ESP32, ESP8266, the S2 and the S3, you'll need a forked Rust compiler. Fortunately, all of our extensor-based chips are already supported in our forked LLVM. So it's just a case of downloading the other compiler. But as new chips come, they'll need to be supported in there too. Our RISC-V based chips are already supported upstream in LLVM, so there's no need to worry about them. So chip support for the standard library or ESP-IDF approach. The general rule of thumb is if ESP-IDF supports it, then so does this approach. There's a little bit of work to do, perhaps adding a new target in the Rust compiler, or perhaps some CFG work to feature gate certain peripherals for this chip, but most of that is relatively trivial. So support comes very quickly to standard library or component-based projects. Bare metal's a little bit different. I wouldn't say it was slow, but there's a few extra steps. So obviously one is we now have to write the drivers in Rust. We can't just use the ESP-IDF implementation. There's also some precursor work to generate a SVD file, because in Rust we use a tool called SVD to Rust, which will take a SVD description of the chip, all the peripherals, what interrupts it has, etc., and it'll generate Rust code that allows you to access these peripherals, and these are called peripheral access crates. And you can see in the second column of this table, pack is peripheral access crate. As you can see from that table, we already support all the chips except for the C2 and the H2. I know for a fact the C2 is being worked on right now, and I believe we have some level of support for it, but it's not been merged yet. So the general rule of thumb is that bare metal will take a little bit more time to support a chip, but in my experience, it's not been that long. So hopefully by this point, you're excited by Rust. Yeah, so I'd like to talk about what we want to do next. So we'd like to upstream our LLVM extensor backend. This will make things simpler for everyone, including ourselves. So we've had the patches in review for a few years, but we're making a really strong effort right now to try and get some more coverage on that. And once it's upstreamed in LLVM, we can then upstream our Rust patches, which will be nice. We've already actually upstreamed our RISC-V based patches because RISC-V is already supported in upstream Rust. So it's just the extensor stuff to do. We'd like to provide Rust bindings for existing components. So we have bindings for most of the core components that actually live in the ESP-IDF repo on GitHub. But we'd like to start offering bindings to important but external components. For example, ESP Rainmaker doesn't live in IDF proper, but it's a very interesting component to use. We'd like to improve bare metal support. This is an ongoing thing, and that would include adding Wi-Fi support to more than just the ESP32 and the ESP32 C3. So the standard library supports Wi-Fi and Bluetooth on everything, basically. Just because we use the ESP-IDF implementation. For bare metal, there's a bit more work that goes into adding support for Wi-Fi and Bluetooth. So at the moment, we only support the ESP32 and the ESP32C3. But hopefully we'd like to extend that to the S3, the S2, and the C2. And there's plenty more. Those are just 3 things that I pulled out from the project board. There's we do all of our work out in the open on our GitHub repo organization. Sorry, ESPRS. So feel free to check out the project board after this. So hopefully you're excited by Rust and you may want to try using some Rust on our chips. We actually have some free training available. So we contracted a company called Ferris Systems to write some training on using the Rust standard library approach to create a Rust project using I believe an ESP32C3, but it should work for all of our chips with a bit of tweaking. And there's a workshop available. It's all online, and yeah, it's really cool. So if you're interested even a little bit in Rust, I would definitely check that out. And I have the link here with some other stuff. So there's the link to the Ferris training. We also have a book, which is a work in progress sort of overview book of the ESPRS effort. This has some installation guides, some debugging guides, an overview of the approaches, so a bit more in depth than what I've gone into today, and sort of how they work a bit more, and plenty more. This is a link to our just our GitHub organization in general, and you'll find plenty of repos in there that I haven't covered today. That'll be very interesting. One of which will be ESP template, and this is a template for a bare metal project. So we use a tool called Cargo Generate as our templating engine, and what that means is you can just do Cargo Generate and the GitHub URL, and it'll give you a set of options to create the project and create the project for you, which is really cool. And we also have one for IDF projects, and this project generator supports either standard library projects or component-based projects, which is nice. Finally, the last link is a link to my blog. So I've been working on this for many years now, and I've been detailing the progress over the years in a series of blog posts. So if you're interested in the history of how we got this far, you can read back through that. I also post an update every quarter detailing the progress over the last quarter. So if you want to keep up to date, feel free to follow that. But yeah, I think that's me done for today. Thanks for listening.